Okay, so let's see here. Okay, so this is gonna be, I think, a short one. I just wanna take the time to really understand what a GPU, how a GPU works, at least beyond the super abstracted black box level. I mean, I understand that everyone says that, okay, GPU is basically like a CPU, but it's very fast at very simple things. So if you can break your problem up into simple components, which in my purpose of research you can oftentimes, then you can get a lot of speed up with the GPU, which translates into, things like you can do things in parallel, meaning you can do 100 times the things you want to do at no extra time, right? Because you can just split up into 100 parallel processes and then just let them go all at once. That's kind of the idea, but I don't know much beyond that. So my supervisor said, and I kind of agree, that it would be good if I could say something about this. Maybe I don't know, just a couple of pages. I don't even know if I can fill in that many things, that many pages with the GPU stuff. But yeah, so let's just go ahead and try to learn a little bit about what a GPU, like what it really is, and hopefully that will also help me understand how my code respond to the performance, right? I mean, well, to my implementation, I guess. Okay, I'm in a mess. I don't know what I'm talking about, but okay. I pull up some links. I don't really know if they are relevant, but they look relevant. So I'm just gonna start reading quickly. Can you see? Let me. Yeah. Okay. So let's not be slow about this, because I don't think this is gonna be super. I mean, either I'm gonna get it really fast, or that there's very little hope, because if they start needing me to look into, I don't know, like deep computer architecture stuff, then I can just I don't know. I don't think I can do that anyway. Okay, GPU, blah blah blah. Common CPU is optimized to be as quick as possible to finish a task at as slow as possible latency, while keeping the ability to quickly switch between operations. Its nature is all about processing tasks in a serialized way. What's this? This is a blog by someone. Okay, then let's just read it with some reservation as well. Okay. Yeah, so this is GPU has many little boxes. CPU has very few boxes, but the boxes are bigger, I guess, typically, so you can do bigger things. I don't know. Okay, this looks useful. This looks useful. Let's see. Core. Actually, what's a core? I mean, I roughly know, but really, what is a core? When we speak of cores in NVIDIA GPU, we refer to CUDA cores that consist of arithmetic logic units. Okay, so each core has an arithmetic logic unit. Is it? Both use the memory constructs of cache layers, memory control, and global memory. Okay. Both use the memory. Okay, by the way, I have no background in computer architecture whatsoever, so this is completely new stuff to me. Let's see how much I can appreciate here. The cache layer, memory controller, and global memory. So I'm guessing the memory controller decides if the thing goes into the cache or global memory, where cache, I think it's a place where you can quickly access it, and global memory, but cache is small, right? Because you can quickly access it, so it's typically quite expensive, so it's small. And global memory takes some time, but it's cheap. So basically I think the cache is something like your RAM, and then this is like your ROM. low latency memory access by using significant cache memory layers. Okay, let's take a look at the diagram. Generic memory focused modern CPU. The precise layout strongly depends on the vendor. Okay, so PCIe bus, don't know what this is. System agent, don't know. Memory controller, DDR4. This is your hard drive, right? Could be solid state, whatever, but yeah. And then these are your core 1, 2, 3, 4 data cache, instruction cache, and then there's this LLC cache. Don't know what this is. Okay. A single CPU, so this is one CPU. Okay. Consists of cores that contain separate data and instruction layer 1 caches supported by layer 2 caches. The layer 3 cache is shared across multiple cores. If data is not residing in the cache layers, it will fetch from the global memory. The number can go up to 28 or 32, runs up to this speed, depending on blah blah blah. Cache sizes range up to 2 MB L2 cache per core. Caches sizes range up to. Wait. Two MB, that's super small, right? Per core. So this is 1, 2, 3, 4, 8 MB. Does it mean GB? No, but that's not right either, right? Because I thought, okay. Well, I might be mixing up cache and RAM. So if any computer folks seeing this, please try not to puke blood. If we expect higher, okay, so this is so far. I mean, I can understand it, but I still have many questions. So we'll bring cores to work, and it's less focused on low latency. Okay. So what am I looking at? Well, what's this? So this is a GPU. So each level 1 cache has a bunch of these little things where there's a streaming multiprocessor 1 and then host. Okay, this is not making any sense to me. Okay, so I have the memory. Is it the same memory? DDR4. This is GDDR5, so it's not the same thing. Memory controller, blah blah blah. Wait, then there's a RAM. Oops. Okay, so definitely RAM is not the same as cache, but okay, this is getting a little bit confusing already. I mean, yeah, what am I expecting? It's a blog post. A single GPU consists of multiple processor clusters. So, what's a cluster? This is a cluster. Oh, this is a cluster. Each cluster contains multiple streaming multiprocessors. Each streaming multiprocessors accommodate a one layer each multiprocessor. So this is a that accommodates a one layer instruction cache with its associated cores. See, this is confusing because I thought that the core is defined by this collection of cache here, but this is saying that accommodates one layer with its associated cores. So one layer of cache can be associated to many cores. Don't know. Okay, typically one streaming multiprocessor uses a dedicated layer 1 cache and a shared layer 2 cache before pulling data from global DDR5. Its architecture is tolerant of compared to a CPU, GPU works with fewer and relatively small memory caches. Reason being is that a GPU has more transistors dedicated to computation, meaning it cares less how long it takes to retrieve. What? Has more transistors dedicated to computation, meaning it cares less how long it takes to retrieve data from potential memory access latencies must, as long as the GPU has enough computations and okay. We're looking at numbers quickly shows you the possibility of parallelism. When examining the current NVIDIA flagship offering Tesla V100, one device contains 80 streaming microprocessors, each containing 64 cores, making 5,000 block cores. Tasks aren't scheduled to individual cores, but to processors clusters and SMs. So, okay, that's how it's able to process in parallel. Now combine this powerful hardware with a programming framework, so blah blah blah. Okay. I mean, okay, very nice, kind of. This is a benchmark for XLA. This is kind of the same thing. Do I need to write this down? Okay. Yeah, there's a lot of terms here. Maybe helpful. See here. What is memory throughput? Like, what's the definition there? Memory is the rate at which data can be read or stored into a semiconductor memory by a processor. The theoretical maximum bandwidth for Intel Core can be about the memory frequency multiplied by the number of bytes of width and multiplied by the number of channels. What? But I thought the point is that it doesn't have high memory throughput. Well, I'm already confused. I thought the whole point of GPU is that it doesn't care so much about retrieving memory. What? Oh man. Okay, let me just revisit this one again. So a CPU's job is to be optimized to finish a task at as low as possible latency. Throughput optimization, as many tasks as possible through its internal at once. Okay. Okay, this looks fast. Okay, let's go. Latency optimized. A wide range of tasks sequentially, while the GPU throughput optimized, specialized design for high-end parallel computing. Oh, so many confusing abstract words. Task parallelism. So if you have 10 tasks and this data parallelism, I'm not sure what the difference is. So if you have 10 tasks, a CPU can run 10 of them sequentially, and a GPU can run 10 of them in parallel, then what? Okay, well, a few heavy cores, many high memory, wait. High memory size and high memory throughput are different things. Jeez. Many diverse instruction sets, a few highly optimized instruction sets. Okay. Explicit thread management, threads are managed by hardware. Okay. Okay. Can switch between a number of tasks quickly. I don't know what it means, switch. Which may create an impression of parallelism. Nevertheless, fundamentally, it is designed to run. Okay, so that means, yeah. So that means it is, okay, so I'm starting to get a picture. One task at a time. Manipulate memory and accelerate the computer for a number of specific tasks that require high degree of parallelism. Optimize for dimensional matrix arithmetic and floating point calculations. It is true for linear algebra tasks. Yes. If your algorithm accepts vectorized data. Okay. Architecturally, has a wide interface and a point-to-point connection which accelerates. It is designed to rapidly manipulate huge chunks of data at once. Is data equivalent to memory? Because you gotta store the data somewhere, right? Or like process it. Is that what it means? Increases the amount of data the GPU can work with in a given moment. In a given moment, I think that's a key point. I mean, I get that the whole picture is to point towards parallel computing, but what does it really mean here? So because it can work with a larger memory at once, it can be pushed through faster? What is it? Switching Moore's law. Okay, now this is the point. GPU also limited by the maximum amount of memory they can have. Although GPU processors can move a greater amount of information in a given moment, the memory access has much higher I don't think data is the same as memory here. So maybe it's saying something like a CPU maybe can work with, say, 1 GB of data, I don't know, 1 unit of data at a given time, but can store 1,000 units. And GPU can work with maybe 100 but can only store 200. Is that what it is? I don't know. Okay, so that's the key differences. Flynn's taxonomy is a categorization of architecture by Stanford. Flynn computer consists of 2 streams data instruction that can be processed in sequence, 1 stream time and parallel. 2 data stream with 2 possible methods of processing leads to 4 different categories. 2 data stream with 2 possible methods to process. Okay, so single instruction, also single amount of. So single instruction, single data executes 1 data stream. This architecture is used in all the computers. Single instruction, multiple data stream. Single has a single and instruction memory, so only 1 instruction can be run. That instruction can copy and run across each core at the same time. This is possible because each core has its own dedicated memory, which allows for parallelism at the data level. Data parallelism. Data parallelism. Data parallelism. Multiple instruction, single data. Why would you want that? Single instruction, multiple threads. Oh man, I feel I should write this down, otherwise I'm gonna forget. But I don't want to spend too much time doing this now. Threads, thread blocks, and kernel grids. Yikes. Okay. A thread. Can I blow this up some more? A thread. A CUDA core. Let me write this down somewhere. I've gone back to papers since a few days ago. So this is a core. Yep, this is already getting confusing. So we have a thread. What? Okay, wait, I think I need my iPad for this. Oh, my pen is dead. That's upsetting. Oh, wait. I think you charge it for a minute what you get and 1 hour use. Is that the rule? Is that a promise, Apple? Okay, let me charge it for just a minute then. So we have a thread which is a core and it's a parallel processor. I don't know what that means. Does it mean it can run parallel things inside it, or it can be run in parallel with other processors? It's a parallel processor. I'm guessing it's the latter, because it doesn't make sense if I have thousands of them and then they all can run things in parallel. It should be that they can run in parallel. Has it been a minute? Okay, it's definitely been a minute. Okay, let's go ahead and use it. Okay. So a GPU. Okay, wait. So let me quickly summarize what I saw just now. Yeah, so far it's a little bit vague, so I'm not gonna say anything specific. So the Flynn taxonomy. Maybe I shouldn't draw, I should write it down. Yeah, this is... Yeah, I'm fumbling here. Let's open Lix. Let's open Lix. Okay, and then that's new. I don't remember the stuff, but okay, GPU. I forgot all my. You know what? I'm gonna just do this on I'm gonna do this on HackMD instead. Maybe I can shrink myself here. Oh, let me sign in somewhere else. Okay. So what's the best way to do this? Okay. Alright. Let me call this let's not bother with minutia here, okay? Keywords. Wait, why is it? Can I copy this? Table. I think this is useful table to have. So it's just a line. Okay. Why is it like this? Yeah, you know what? I'm just gonna quickly do this. So I'm writing this down not because I know what they mean, but so that I know that when I see these words, I should know. Okay, now I quickly go blah blah blah. Okay. every thread in a given CUDA block can access the same shared memory. This is different. Wait. Per block basis. Okay, I'm not sure. Let's not write this down first. I need to know what this is. On the same kernel. Tags a kernel. I feel like okay, never mind. Yeah, I feel like look at the way this block is written, or rather it's going at a top-down type of way, right? It's explaining bigger words with slightly smaller words, and then the smaller words are still confusing, and then you have to read all the way to the end. Hopefully, then you can find out what the hell is happening. Yeah, but I feel like I would do better from a bottom up, because when you say things like memory, I don't know what it means. I can only kind of have a placeholder of the concept in my head while I'm still remaining kind of blur. That's just how I learn. I generally don't like to take some concept, some big concept, and running with it unless I really know what it is. Or have an intuition, which I don't really. Registers. Okay, now this is going to be useful. Registers are memory that gets allocated to the individual threads. Because registers exist in on-chip memory and are dedicated to the threads, data stored in registers can be processed much faster than any other data. Wait, this is memory or data? I don't even know if there's a real difference. The allocation of memory in register is a complicated process handled by compilers as opposed to being by controlled by software. Okay. I don't even know if I want to say such things because I really don't. I'm extrapolating from what I understand, but I don't know if that's a reliable thing to write down. Read only is on memory, chip memory. On the GPU streaming multiprocessors, it is used for specific tasks such as texture memory, which can be accessed using CUDA texture functions. In many cases, fetching data from read-only memory can be faster and more efficient than using the global memory. I don't even know where to put this. Okay, L1 memory and shared memory. L1 cache is on chip memory that is shared within thread blocks. Okay. So there are different things. Can be accessed. All threads are full. Can make all threads. Okay, I think actually reading this now, if I read back the previous blog, it would be quite a bit more easy to understand. Clusters. Is cluster same as kernel? And is streaming multiprocessor same as block? The CUDA architecture. The CUDA architecture is built around a scalable, multi-threaded. When a CUDA program on a host CPU invokes a kernel, blocks of the grid are enumerated and distributed to multiprocessors. Are enumerated and distributed to multiprocessors with available the threads by a thread block execute concurrently on one multiprocessor. Wait, this is a bit confusing, huh? Because seems like they are not talking about the same thing at all. Seems like threads and processors are kind of so is thread a physical thing, or it's a physical thing, right? But why is it being described as like an abstract thing? When a CUDA program on the host CPU invokes a kernel grid, oh, I should just read the CUDA version, right? Oh my god, what am I doing? Oh shit, though. This is gonna be a while. Well, I don't expect anything less, actually. Son of a gun, though. Oh, no. Okay, let's see how much I have to read then. Jesus Christ. How long has it been? About an hour? Okay, I think we can spend a bit more time on this. Okay, let's dig in. Also, this is super small. Oh, there's a PDF. Does it help? I mean, oh my god, it's 400 pages. It's a freaking book. Yeah, I think I need to at least understand the programming model. The memory stuff looks kind of useful, but I don't know if I absolutely need it. Okay, so, alright. Here we go. Yeesh. You know how people play speed, I don't know, like how people do speed things like eat a lot of food or speed run in some games. I need to speed learn this. And the thing is, I don't really know how much I need to know. That's the that's the funny part. I guess I want to know enough so that I know what's going on if my code is not working or it's not working as expected. Again, that doesn't really tell me much, but so I basically gotta learn about how memory is passed in and out in a yeah, and then how I can distribute, how it is being distributed to the different cores supposedly. So this is just super introductory stuff, you know. I got my alright. Like even right now, this node is poorly written and constructed. I'm pretty sure, you know, in a month's time when I look back at it, I'll be glad that I did this anyway. Okay, so each core, so these are multiple cores, so I guess this is a block. Each block share the same L2. Wait, no, sorry, wait, all threads in all blocks. All threads in a block? Maybe that's not accurate, huh? No, yeah, so this makes sense because I see so I'm guessing this is a block. They have cores inside. This is a grid. No, this is a grid, yeah. So wait. This is a core. Wait, what about L1? So this is a block, yes. So this is a block inside its cores. This is a grid, I guess. and then all the blocks can get into L2. And then there's L3 and DRAM, and then there's L2, I don't know what this is, and then DRAM. Okay. The GPU is built around an array of streaming blocks of threads that execute independently from each other, so that GPU more multiprocessors execute in less time than the GPU few multiprocessors. So multi-threaded CUDA program will be displayed into blocks, and then the blocks will be executed by I see. So these are the parallel processors. So it depends on how many blocks I am. So this block I think is VMAT, right? And then 1024. Is that what it is? 1024? How I need to check how many GeForce what? Oh shoot. GTX 1080. Because the number of maximum so, but if it's parallel, that means it should be like this. What is this motivational speaker music I'm listening to? This is like the award show that hasn't started, or like the dinner and dance. One paragraph. Threading. Yeah, threading is not a good idea. This is important. Turning matrix multiplies into batch multiplies. That isn't always the best way to compute things. For example, if your code is embarrassingly parallel, you're using VMAT without collective communication, and you have many cores available, rather than plumbing that loop down to every operation and relying on the compiler to fuse operations back together as needed, it might be better to keep the maps loop at top level and then schedule it to multiple cores. For example, if you're running parallel MCMC on CPU, that's probably a better approach. You can do that with PMAP. It's a bit often P is designed for mapping over hardware resources, but more often it's used to map over multiple hardware accelerator cores, like multiple GPUs. Then we rely on XLA GPU to manage parallel resources within each such device. First, you have to tell XLA to create separate CPUs devices rather than viewing your computer's one CPU. Then, when you use PMAP, your program instances will ultimately be mapped to distinct OS threads and thus hardware cores. One way to force access CPU is to use a shell environment so that you This is CUDA. Shared memory. So each block. No, this is one GPU. Or is this one block? Should probably talk to Waiho. Three component vectors so that the threads can be identified as using Wait, I'm so confused. Ah, I know what's wrong. Yes. Yes. Oh man. QA. I don't know what to call it. Shows increase in time. How do I add a code block? It's not parallel.
What do you mean test FN parallel is not defined? Oh, no, no, no. Okay, so there's that. Okay, there's that. Okay, let's keep on going. Oh, I'm quite tired.
But I think tonight I can already start testing the work. I'm so tired. You know what, I'm gonna take a little break and no, if I take a break I'm just gonna be lazy and then it's gonna be too close to dinner, I'm just gonna eat and then let's not take a break. Not now. Okay, not now. Alright. Okay, I don't really know what's happening because I forgot my C++, but okay, it's a vector add function that takes ABC and then global function. That when called are executed n times in parallel by n different threads as opposed to ones like regulars. What do you mean n times in parallel? Literally n times by n different threads, so n time. Okay. Okay, a kernel is defined using the global declaration specifier. So that means if you have something that you want, let's say you have something that you want to run 1,000 times, what you do is not to write a loop or something for 1,000 times for it to run 1,000 times. What you do is you write the definition once as a kernel, and then it will be run by 1,000 threads. And then I guess you have to do something to say that it's 1,000, but that's the idea. You write a unit, and then the replication of it is taken care of by the hardware. I think. I'm saying this so that maybe I rewatch this down the line and I can remind myself. Okay, so the number of CUDA threads that execute the kernel for a given kernel call is specified using the triple what do you call it, brackets, we call it parentheses, brackets, braces. What's this? Sharp brackets, angle brackets, is it? Oh my god, no. Bracket symbol. Square bracket. Angle brackets. Yeah, so it's angle brackets. Okay, wait. Let's be distracted here. Bit of digression. Chevrons. That's a fancy ass name. Triangle bracket, pointy bracket, brockets. Left and right caret. Tuple. What the heck? Guillemets? Guillemets? Chevrons. This is just curly brackets or braces. Accolades. Top two board. Squirrely brackets. Seagulls. Oh yeah, they do kind of look like seagulls. What about the square brackets? What do they call it? Crotchets. And parentheses, I guess. Circle brackets, smooth brackets, parentheses. Okay, so that's my 2-minute break. So I need to tell you how many to run using this new execution configuration syntax. Each thread that executes the kernel is given a unique thread ID that is accessible within the kernel through built-in variables. Okay. The following sample code using the built-in variables built-in variable thread IDX.x adds two vectors A and B of size n and stores the result in vector C. Invocation with n threads. What is it 1? Why is it 1 and n? It takes two vectors A and B of size n I need to learn this actually. This is 3 component vector. Wait, so thread IDX? What the hell is thread IDX? Ah. The thread index within the block. What? So, oh, okay. What? And contains the thread. with smaller batch sizes and using. Yeah, so it's a vector and it contains the thread index. So threads can be done using the one-dimensional, two-dimensional, three-dimensional thread index, forming one-dimensional, two-dimensional, three-dimensional blocks of threads. So this dot x spurious timing. Oh, could that be relevant? Yeah, my co-supervisor suggested that I play with a profiling tool, which is actually super. What am I doing again? I'm like all over the place. Yeah, I don't know what's going on. Manual capture, profile. This starts the profilers of a TensorBot. I'll do this later, but let me check that. Actually, I don't think I really need this much. A little bit confusing, but okay. Yeah, I should look into this. How to say? Okay. Why is it in my Python 36? Oh, I need to, which I need to Python dash m pip, is it? Python dash m pip install TensorFlow TBP nightly. Yep. Great. Okay, I'm gonna get this done, hopefully. And then if I'm done, then I take a break. It's been 3 hours. Okay, I think I can, definitely do another couple of hours later tonight. I'm trying so hard to be productive. It's tiring. If you have TensorFlow installed, blah blah blah, we recommend TBP nightly because like some there. I don't know what the difference is. Okay, you can instrument your code to capture a profiler trace via the profiler start trace and stop trace method. Call start trace with the directory to write the trace files to. This should be the same log dir directory used to start TensorBoard. I don't know what this should be the log dir directory used to start TensorBoard. Then you can use TensorBoard to view traces. TMP. No. As an alternative to start and stop trace. To view trace, first start TensorBoard if you haven't already. Okay, let's try this out. This looks interesting. Never tried this before. Okay, so I need to /tmp TensorBoard. Okay, I think that let's just use a new code. New. Let's call it TensorBoard. TensorBoard test, and then all we really need is this code, and then this. I think that's it. Oh. Hi, Cheese-toe? Yeah, I am. Sorry, I can't read your chat. I've never seen this category before. What do you mean? Like on Twitch? What category? You streaming under math? Yeah. Oh wait, do you mean you've never seen this category on Twitch before, or that I am streaming under the math category? Because in my understanding, there's almost no math content. Not that I can find anyway. So yeah, this is not exactly math, but yeah. Usually programmers, science and technology, or software programming. Right, I mean, if you're software programming, then I think it makes perfect sense. But yeah, I'm a research student in statistics and like computational stats. So now I happen to be dealing with having to profile my code, because the GPU runtime is very troubling. Don't know what's going on. Yeah. Oh, nice. I assume therefore you are currently a student. Wait, no, I'm gonna put this. I'm gonna put this here. I'm gonna put. I'm a mess. Then go for a master's degree next year. Oh, that's great. Yeah, that's great. Yeah. In what field? Maybe I should try science and technology. Maybe that will make my content more accessible. I don't know. I'll get my bachelor's degrees in computer science. Oh, that's great. Oh, that's super relevant these days. Is there any part of comp-sci that you're interested in? Like like algorithms or OS or security? It's quite a lot of specializations. 30 times 9 problems. Okay, what am I supposed to do again? I forgot. Kind of a buzzword these days, like machine learning, currently interning under a biotech firm. Oh, that's great. Well, my background in my bachelor's is actually engineering. I don't think I knew any stats in undergrad. I mean, yeah, the engineering math that I learned is like calculus and things to do with numerical computations a little bit. Yeah, it's only after I graduated that I had some time to think about what I want to do, and I got into machine learning as well. Then I eventually figured out like stats is a bit of the background behind machine learning, and that's super interesting. Yeah. ML to predict protein functions. Oh, wow. How would you even go about doing that? I have no idea. Predict protein functions. What does that mean? like what a protein does? But anyway, that sounds really cool. What type of ML techniques do you use? Like is it like a deep learning thing, or I don't know. There's a bunch, right? SVMs, I don't know. What do people like these days? People like transformer networks, right, these days? Yeah, they love that. And like optimal transport, I think. People are into that. Okay, wait, let me see what my soup is telling me. I think the example probably is saturating the parallel capacity linear increase. But why is it linear though? Doesn't make any sense, right? Given a large difference in single performance, the point at which saturation is reached probably have required 30 times to see similar trend. 30 times. 30 times. So I'm looking at 200 30 times. Up to 30 times. That's an interesting way to put it. So if I do times 6, 30 times, I get 6,000. That's an interesting claim. Can we do that? Oh shit! Oh! It's true! Are you connected to a VM? No, I'm not using a VM. Depends on what you mean. I am running the code from a computer cluster in the university servers. But my Ubuntu is just my Ubuntu. Yeah, I don't dual boot into anything else. It's been a long time since I've seen Windows. Yeah. Okay, yeah, so I think tomorrow I can talk to my supervisor about this after I've done a few more tests. Why? But why? Oh right! Oh my god! What am I thinking? Of course it's linear. I'm so stupid. Wait, what the heck is happening though? What is this? What are you researching? My research has to do with Monte Carlo, Markov chain Monte Carlo sampling. So it is essentially based a lot on statistics and, well, not so much on statistics and more on probability distributions and things like that. So yeah, so the goal is to sample from probability distributions, and it's not trivial at all to do that. So right now, and I'm trying to run, so these things called Markov chains, and I'm trying to run them, and I'm trying to do, sorry, MCMC sample something, yes, but I'm not particularly attached to any application. I am working on, some variations of existing MCMC methods to look for improvements and efficiency boosts. So right now, this algorithm I'm working with is not here, you're not seeing it right now, but one of the main points that I'm trying to get at is that it can run in parallel, which is harder to say for an existing method. There's an existing method called Hamiltonian Monte Carlo, HMC. It's more or less the most kind of standard popular method, and it works quite well. But some of the things, it comes with some challenges to use it. And the steroid version of HMC is called NUTS. It is basically HMC, but it has all those automatically tuned parameters. But that automatically tuning part makes it hard to run in parallel, and it's expensive to run. So I'm trying to prove empirically that I can beat HMC in that sense. Okay, so this is here. Wait, let me, where's my single precision of sigmoid. So now let's try something different. Let's go to 6000. And yeah, let's do this. Should be fast. I remember writing a Monte Carlo tree search for reinforcement. Oh, yeah, so the Monte Carlo, the concept of Monte Carlo is super general, right? It basically just means that you you do things a bunch of times. That's about it, I think. So, yeah, there's a bunch of Monte Carlo based methods. Markov chain Monte Carlo is just one of them. Yeah. Even though Monte Carlo tree search has very little to do with what I'm using. Yeah. Reinforcement learning, nice. So you use reinforcement learning to learn the policy to predict the protein function? Okay, I understand reinforcement learning. There's like a few flavors to it, right? Some like, I don't know, policy based, agent based, whatever. But what? So what's the goal of? In any case, it's cool. But this is cool. No, that's not related to my internship. Yeah, I see. Yeah. Oh, okay, right. So you plan to research in machine learning, I guess, not necessarily proteins. This is interesting. Why is it like this? Let's try. I was implementing the mu0 paper. Whoa, how did that go? I'm a huge fan of chess, by the way. I mean, I don't actually play Go. I'm trying to learn it, and I don't have time. But yeah, by keeping a close eye on some of these news. Oh, yeah. Actually, now that you mention it, they do like a MCTS and then reinforcement learning, right? From no rules, yeah. Is it hard to implement? I assume I don't know. I assume that it's super big and takes forever to run and it takes, I don't know, like a terabyte of GPU or more. I've tried to learn these things many times, honestly speaking, like reading blog posts or the paper itself, and I do it every time I come across it, So I read it for like half an hour and I got tired or I can't really understand it, and then I give up. And then a few months later I come across it again. I'll read it again. So each time I get further, but between each time I also forget a lot. So yeah, okay. Yeah, unfortunately I can't say that I have a good understanding. At a academic level at least, I can roughly see what it's trying to do. But I got pretty far. No, that's good. Yeah, that's good. You should you should put it up somewhere on a GitHub or something, so that when you have time you can go back to it. I don't know. Yeah. One thing that I learned from my research is that you should always put stuff out. If you learn something, write it down. Even if it's just a few paragraphs, write it down. If you have some code, put it up. If you want to explain yourself something, make a video, put it up, and then you will find it useful down the line. Because you forget a lot of stuff. I forget a lot of stuff. So, this is cool. What? 5,000%? So on average it performs 5,000% better than what? Oh, human performance testers. So it's so it's 50 times better than humans. Is that what it is? Oh, for Atari. What's Atari? Oh, is it like the it's kind of like Go, is it? Oh wait, Atari, like the game console, Atari. Wait, am I missing something? Oh yeah, actually the console. I was thinking about shogi, I think. Cool. Oh, what was I doing again? Oh yes, yes. I don't know about theory of deep learning. Oh, I can't read this. Optimize your point, then you do lines of code and automatic differentiation. Yeah, I agree. Well, depends on the research that you want to do. You might not need to know that much theory, but in general, I feel like theory is the thing that will last. So, when you have the newest, the most shiny, I don't know, computing framework or algorithm come out, theory is the thing that's gonna last. So in research, I think it's kind of important. But yeah, things like optimization, probability. I guess for machine learning, optimization and statistics are probably the most important things. And these days, geometry is kind of popular too. When you think about KL divergences, to really understand it, in your variational autoencoder or something, your KL divergence or Wasserstein distance, all those stuff, they fundamentally come from optimization and some geometry and probability actually, yeah. Feel lost when I read a new paper. Oh, I mean, you are gonna feel lost. I mean, I've been doing this for several years and I still feel lost, so it's normal. Just don't feel discouraged. Even you can't understand a lot, you should just try to understand a little bit at least. And oftentimes that's what it is, yeah. I mean, yeah, if you think about it, the author spends maybe a couple of months working on the work, scrunch it down to 10-20 pages. It's hardly possible to explain everything clearly, so it's not surprising if it's not so easy to understand. And of course, there's a lot of poorly written papers out there, so you want to be careful about that as well. Like, reading badly written papers are actually quite painful, and it hurts your understanding, so sometimes that's counterproductive. Yeah. My supervisor recently shared me this paper about the NIPS conference, NIRIPS, about, let me see if I can find it. It's about how NIRIPS, where is it? Random? Yes, the inconsistency in conference. Yes, this one. It's basically saying that if you're accepted to NIRIPS or super high level conferences, actually might not mean a lot. Yeah. Yes. So the impact of the paper is not super related to the acceptance to these venues. Yeah. And then, yes. This part, it says, finally, wait, let me see if I can blow it up. We suggest that the real conclusion of the experiment is that the community should place less onus on the notion of top-tier conference publications when assessing the quality of individual researchers. Boom. I mean, for someone like me who's like a super small-time nobody, this is happy news, I think. I don't know. It's like, oh, hey, you don't have to be Google to be good. Anyway, okay. This is an interesting curve. I don't really expect this actually. What's happening? Okay, I think this comes from, this just comes from me not understanding very well what GPU does. Okay, let me carry on. need to do this. Need to fix this. Yeah. And I apologize if you see some very badly written code. I'm not a very good coder. I do okay, I think, but nowhere near like commercial standard code. What am I doing? Project streets. Okay, I'm just gonna randomly try what it's saying here. Don't know if it's gonna work. Do I really have this even? So I want to start my trace. I guess let's say start here. Does it work? Does it work? And then you stop trace at the bottom, I suppose. I'll be really surprised if this works, because nothing I do works, so this should be the same. Okay. Okay. Stop tracer. It never works the first time. Yeah, that. Yeah. Yes. The real thing you learn in research is not all the stuff that you learn, because those stuff, honestly speaking, if you don't use it, you're gonna forget it. But what you really leave with is an undying spirit, and you don't give up. Because it never works. And you just gotta keep on going. Wait, why is this so slow? Am I doing something wrong? It says idle. What the heck? Oh, no profile started. What? Did I not start that? What do you mean there's no? Wait, am I high? What the heck's going on? Oh, I could use the... Maybe that's a more sensible option. No, but yeah, you know what, I want to... Yeah, wait, let me just restart this. Oh, I don't think it works in yes. Okay, I think I need to do it in one block. Maybe it doesn't work in Jupyter. Yeah, actually I'm quite sure it doesn't work in Jupyter. That's kind of the issue here. Okay, let us do this. Now this works. And let's do from 1 to 10k and 10,000 cycles. Yo, something wrong already. Profile has already started. Only one profile has been run at a time. Okay. I should be able to view the trace start TensorBot if you haven't already. I have not. Let's see, how do I do this? Okay, so I'm in my... Oh, it works. Hey, what's up? What's up? Okay, then I can start my tensor board. God, I hope this works. And then it should give me a link. Oh shoot. Wait, is there something wrong? Oh no. Oh no, oh no, oh no. Could not open dynamic library. Jesus. Oh shoot. Oh, yeah, sorry. Hey, wow, there's 2 people, it's a crowd, that's 3 of us. Hi, Torpedo Cloud. Yeah, I've been extremely occupied with my research, so unfortunately I don't have time to stream chess. I still play quite a bit, but it's mostly for de-stress. Not sure how that works actually. Making myself think a lot to de-stress, but it does the job. Magnus signed the chess championship contract. I don't know. I have no idea. I know Nepo signed with chess.com. That's about it. Signed and who won the thing recently? Is it MVL? He won something? Okay, wait, what's happening? Cannot download some. Please make sure the missing libraries are installed properly. Install GPU. To hold down setup required. Skipping registering GPU devices. Could not load dynamic library CUDNN so.8. What? No such. Yeah, why would it be .8? Am I not on like much higher versions? .8? .8? GP. What? I have TensorFlow, right? Of course. Serving tensor board. Skipping registering GPU devices. I don't know what that means. Like, does it mean I'm not looking at my GPU, but I want to, right? That's the whole point. Cannot download some. Please make sure there's something if you like to use GPU. Okay, doesn't matter. So let me open another one, and then let me SSH into 6006. Okay. Oh shit, it kind of works. Wait, No active dashboard. God damn it. God damn it. God damn it. Of course it's not. Oh, it's here. Ah, it works. Okay. Whoa, what the heck is happening? Okay, wait, I don't know what's happening. Magnus Cosine Science World Championship contract. Alright, let me check that out. What does it mean, World Championship contract? What does it even mean? Wait, so this just means he agrees to take part in the World Championship? Ah, okay, so he wants to show some logo and blah blah blah. Okay, I mean, it would be surprising if he doesn't play, right? It would be a baller move though. The World Champ was like, nah, I'm good. At what the hell? Is it like a GPU usage? Deallocation, peak heap usage, high watermark in lifetime. What? Yeah, for some reason I thought profiling the code is the hardest part, but how about I need to know how to understand any of these things? What? Wait, what? Oh yeah, because I have very little usage. Is that what it's saying? Requested size is small. Okay. But how do I Oh, you know what? I can do this. Peer location. This thing. Let me try this. I don't know if this is true. Is it?
4. I should go eat soon. I don't know if this is... Okay. Parallel GPU programming seems hard. I'm not, yeah, that's the thing. I'm not really programming any GPU, any crazy things like that. I'm just trying to interact with the API that supposedly allows me to access the GPU. But yeah, it's a bit tricky. It's not so straightforward really. Okay. So I should. But how? This is kind of useless, right? If it doesn't show me the why am I looking at it like this? GPU host. Eh? Which one is me? Oh, this is the time. Oh. Yes. Yes. Yeah, but this doesn't show me anything. Steps. What? Dude. Okay, let's go for overview then. Why is everything 0? Am I not running enough things? That's not right. Output. What? Block until ready. Oh, is it because I did not block until ready? No, I did. No, I totally did. Totally did. Trace viewer. You can use WSD to navigate the trace and click, drag, and lens. Okay, trace viewer, let's go. Oh, something's happening. Oh, something's happening. Oh shit. Oh no, something's hanging. Yo, yo. Hello, look at this. Okay, I don't know what's happening, but something's happening and that's good. So I'm trying to profile my code to see what is taking, or rather what resources are being used for what part of the execution. Oh wow, this looks yes, of course, I see. What am I looking at? What? So this is a timeline. Okay, wait, so device, host CPU. I don't really care about this, I think. I want to look at this. What am I doing? So you can see I can use WASD, right? Wait, but why can I not drag it? Can I not make it bigger? Okay, maybe there's just not much to say there. But what's this? JIT test scan. Oh, I see. Okay, so these are the processors. So I'm running these a bunch of times. Yes. Then what's in between here? What's happening? Nothing selected. Tap stuff. What's that? What's that little sliver? Metrics? File size stats? Dude. Oh, something happened. Okay. What am I looking at? What is all these numbers? Oh, no, it's tripping out. Okay, wait, I have an idea. Okay. Wall duration. So if I look at my code, hey, what the heck is my code? Yo. Yes. And if I print the T chains all, you should see that. Okay, now it makes sense. Yeah, okay. Yeah. Oh, can't believe I actually got this to work. So this is 0.33 seconds, which is the wall time for this. So I guess the point, I'm not sure what the point is actually, but I'm guessing the point is to see how long things are taking. What's this? Tree fry split. And then the next one takes that much time. Oh wait. No, it doesn't. 4.2, 4.6, 4.9, 1.67. Wait. What is happening? What is happening? So I expect the runtime to get slower and slower as I increase the size of the file. Yes. Tree. Oh, what's this? 3.615. Whoa. Okay, I think I need to be a bit more strategic because right now I'm not sure what I'm looking at. So how about let's test 6,000 onwards, and then let's just test a few processes, right? Okay. And then let's run this twice as long. And then let's just make it very clear that I wanna have this here. Actually, for the purpose of this, I should just use one chain actually. So let's get rid of this. Let's move all of this back. I can get rid of this. Then just do this. Now this should be good. Now I should see 4 dots linearly growing up. Very good. And then if I look here, and refresh a bit, is it? Data could not be loaded. What? Failed to fetch runs. What did I? Oh, what? Wait, did my... Oh, shoot. Unsafe inline, what? Illegal content security policy, what? What? Okay. Okay. Yo, what is up? Did my... Oh, my network closed. That's upsetting. Okay, yeah. Okay. Yes. Now I get this, and then I look at the trace viewer, and then all that magic is gonna appear, and then I should see 4 processes, each one taking longer than the previous one. That's about all I can tell. Okay, wow. Sheesh. JIT test. So yeah, you can see here takes, if you look at the time, it's about 4.9, and then this is about 5.6, and this is about 6.3, and this is about 7. Okay. Do I? So I think these are then the different things that, you know, like all these test vectors, whatever. So this is the XLA modules. There's one thing that happened at the start, which I think is this line. and then one thing that happened after the first one that doesn't happen again. Yes, all these little things. So technically every single line of code should appear here, and that's kind of cool. That's kind of cool. But they don't really say what they are. Oh. So for example, oh, what the heck, there's so, oh, hello. Oh, Jesus. What's this? Random split. Wait, why is this on CPU? Oh? Host CPU? Wait, this is telling me something. Lex? prng.py split. Next numpy tile. Okay, interactive shell. Wait, but I don't understand what I'm looking at. Host CPU. I guess I show CPU's ops. Oh yeah, but that's interesting because I expected everything to work in GPU. Or does it not work like that way? No, yeah, I don't think it strictly works like that because GPU is gonna be dispatched to the linear algebra stuff, and if it's not linear algebra stuff, I think you can't really do. But wait, that means it's not on. Oh, this is interesting. This is very interesting. So for example, it is telling me that I think that this thing created, this variable created here is actually on the CPU and then it's being put on the GPU. Can I check that? Check device checks. Can I do that? It could be like Torch where you have to send the data to GPU explicitly. Yes, that's true. Actually, I mean, yeah, no, you're absolutely right. Except that, given that if you see here, if I look at the type maybe. The type here you see is a jack lib blah blah extension array device array. So this means that it already lives in the GPU. So it could mean that when it's created, it then is sent to the GPU automatically. I'm not sure. Device buffer device. Yeah, but I get what you mean. I just thought that it is created on the GPU itself, but yeah, you can see it's on the GPU. But maybe there's a need to be transferred. That makes sense actually. Hmm. Hmm. How do I wait? Can I save this and then show it to someone? Heck is this? If computing a normal distribution would be on GPU, or computer storing it there seems unlikely. Seems normal distribution would be a GPU. I don't know. I actually don't know. It's not that you're computing a distribution, you are drawing a random sample. So it's like your NumPy random. And there's also these things like split, which is split is just something to do with random the RNG keys that JAX deals with it a bit differently. You have to take a key and then you have to manage that key. And it doesn't update automatically. So it seems like these things are done in the CPU. What? Yeah, I'm not terribly sure. So for example, all my variables, right, all my vectors live in the GPU. So I then therefore think that, oh, okay, so everything is on the GPU. But now that I look at this, it could be that to run these things, let's say things that I don't know, reshaping a matrix, for example, I don't know, then maybe it needs to be copied back to the CPU, operated then, and then put back to the GPU, because GPU after all is good for, you know, like the math stuff, but not these things. That's my best guess at the moment. What is this though? Tree fry split. What? Split, no idea. Oh wait, this. Oh, what the heck is happening? So there's a bit of things at the end. Sorry, what are you? What are you? Oh, wait, what? Seems to be the case, but what's the point of putting it on the GPU load if you're using the CPU to compute it? Yeah, you're you're right. Shit, you're totally right. Yeah, I mean, so in that case, seems like the way to do things is that. Wait. Yeah, so maybe when you need it to be on the GPU for linear algebra stuff, then you put it on. Then you don't need to take it off. I mean, I understand that when you save it or you print it, something like that, you need to have it on the CPU, but I didn't know intermediate operations could be affected too. Yes. But yeah, okay, I need to just see if am I able to see if it passes between through this profiling. I should be. Trace viewer. In any case, the bulk of the work you can see is done by these things, so it still makes a lot of sense. It's not taking forever. But but that's right now because the data is small, right? What if the data is big? And I need to pass, you know, gigabytes of things. It's gonna be a problem, isn't it? I don't know. Yeah, okay. This is a bit strange. Okay. Wow, look at this. Shit. Huh, interesting. This is okay, cool. I mean, pretty happy that I got all these at least kind of try it out in one afternoon. Alright, I'm gonna go get some food now. So thanks for everyone tuning in. Yes, and yeah, good luck with what you're doing. Alright, see you guys.